So we had this is a vector, this is a vector function of a vector, so there's n of them. So these guys generate a matrix. So we have, and I'm just gonna call it, comes in df of x0, I of j, so n by n matrix, df sub I, dx sub j evaluated at x0. So that's a Jacobian matrix. And we can write this whole thing now as a matrix equation, as we did last time. So now we can say dx dt equals f of x0 plus, and that's vector, plus df of x0 being a matrix, and then x minus x0 plus higher terms that are concerning us. So that's just the expansion of a function, okay, on the right side here. What we did next was if f of x0 equals 0, then we'll go ahead and I'll just choose a vector y equals x minus x0 as a small quantity. And then we have y dt equals, and rename it, well, d x0 times y. And it's a matrix equation, so work it up for d y equals a times y, right? We've got n by n matrix. And it was in this form that we said, okay, yeah, we've got a matrix equation, we've got an eigenvalue problem. And then the homework assignment, we did the eigenvalue problem for something like this. There, the left side actually came from the second derivative, but didn't matter. We still have a nice eigenvalue problem for you guys to work on. We did this yesterday in the recitation pretty thoroughly. Good, so we have that. And again, this is the linearization. Now I have a couple of related things that we can do here. And I'll make this a homework problem. We'll put a couple of these down and we'll do one together just to see how that goes. So here, homework. Suppose we have f of r theta and phi. So we'll take those as, x1, x2, x3 in that order, equals r sine theta cos phi, or sine theta sine phi r cos theta. So you guys recognize that. That's a coordinate transformation, but it's also a vector, a function. In fact, the arrow on here, be clear on that, right? So the homework will be to find the Jacobian matrix of this, calculate df of r theta phi, and its determinant. So that's a nice well-defined problem. It's related related to this. And what I'll do is I'll just do the simpler example that goes with it. Simpler example that goes with it would be f of r phi equals r cos phi r sine. These were the spherical polars, these are the plane polars. And that df of r and phi is going to be df sub 1 dr df sub 1 phi df sub 2 dr df sub 2 d phi. So that's what we're shooting for here. And that matrix is f sub 1, f sub 2, so we'll have a cos phi, and then we'll have minus r sine phi, and then df will have a sine phi, and f sub 2 dr cos phi. So that's what we're looking at, except the 3x3 version of that. What about the determinant of this? Determinant of df of r and phi is r cosine squared phi minus negative r sine squared phi equals r. You might even guess what's going to come out on this one if you want to calculate it. This is how you get, this is the general way of getting the volume elements in multivariable calculus, different coordinate systems. So it's a good one to look at too, related to what we're doing. Let's see what else I have listed here. This one is slightly related. Okay, good. So there's a problem for you guys to do just along these lines, a little complicated. And another one. Somewhat related. I have to leave this one under my notes. So the next thing, and we'll make this a homework as well. What we're going to consider is f of x. So now it's one variable f, but n variable x. It's going to be the scalar product of x and a matrix C times x, where C ij equals Cji. So it's a square matrix. Cij equals Cji. Cij are all real, so it's a real symmetric matrix. That is to say, real symmetric matrix. So another way to write this is f of x equals double sum ij Cij xi xj. So this is just a general quadratic form that's generated by a real symmetric matrix. we want to do, and I better look this up here, we want to show that we can expand this. So homework, I have to consult my notes on this. Show that f of x plus c, and I equals 1 to n, j equals 1 to n. So show that f of x plus c can be written as f of x plus what we're trying to do is show that this is this plus a linear term plus something that's the order of c squared. Okay. Basically, that shows that you can linearize this kind of thing. So I have to consult the book here. Generally speaking, we want to have a linear term right here. The idea with linearization that we just said, we want the linear term. The linear term in this case is going to have this form. A C where this vector A is equal to 2 times that matrix times the vector x. And you're going to have to make use of the symmetry of this thing. And then what's going to be left is all terms of c squared form. And since we're thinking of that as a small quantity, this actually goes back to the fundamental definition of differentiability, which is that we can linearize where A and A, comma, C is a linear mapping. So this is a nice one. You have to make use of the symmetry here. And what does this linearity mean? So the linearity means A, comma, alpha, C plus beta, zeta. These are all n-component vectors. Alpha and beta, or numbers, would have to be alpha, A, C plus beta, A, zeta. So just for the record, right, the C vector is 1 to n, and the zeta vector is also zeta 1 to zeta n. So this is a linearization of this quadratic form. And if you look at this carefully and think about it in one dimension, it's really the linearization of this simple parabola. But this is now n variables, and there's more going on. So yeah, let's put the equal 1 to n for the record here. And so yeah, this is a homework problem, and the hint on how to do it is actually this. You just are very literal with this, right? So here's the definition. So you can actually go into here, right? Once you recognize that this scalar product gives this double sum, we've done that in class before. Then you literally go in with x plus c in here, component-wise, and start multiplying it out. Actually, it might even be easier to go in with x plus c in here. You're gonna get some mixed terms that seem to have the wrong order, but that'll be resolved with the symmetry of the matrix. And then you'll end up with, this one is gonna look something like c times c. And since these are small quantities, in the limit, basically these two are the linearization, and this is the quadratic remainder, so to speak. So you always want to see these complicated things as familiar objects. So suppose you had n equals 1, that f is equal to cx squared. And you drew a graph of it. It's going to look like this. And then if you take it at some point, which I'll also call x, and linearize, you would be constructing this point slope function, and then you have your quadratic in there as well. So the n equals 1 case is really clear that n greater than 1, you actually have to make use of the symmetric matrix in order to achieve this form right here. Okay. So that's a good one. Let's see what else we have on our plate. Homework problem is that. Good. The third one on related topics. Good, so this one here. So now, I'm gonna put this on homework as well. We may do this one together right now. But now we're going to look at f of x, where you take an object from R to the n and map it onto the real numbers. And an example of this would be f of x1, x2, x3 is simply equal to x1 squared plus x3 squared. It's the magnitude squared of that vector in R3 space. So we can still visualize this thing completely. And suppose f of x is equal to a constant. So what we have then, in our example, we can have f of x1, x2, that now? What is that object now? So the restriction of these three variables, the sum of the squares equals r squared. That's a sphere in 3 space of radius r centered on the origin. Sphere r centered on the origin. So what we want to show is, and I'll go back to this formulation right here, I've just been doing that example. If f of x equals constant, then gradient f of x is perpendicular to the surface. F of x equals constant to the surface. And then we want to prove that the gradient of f of x is perpendicular to that surface. This is a good one. Okay. So in order to, this would just be the abstract formulation, f of x, right? Real value, you have a constant, it's a surface, and then the gradient is perpendicular to the surface. But with this concrete example, you can actually see what's going on. So let's draw a picture. Here's our sphere, x1, x2, x3. What's the gradient of f of x? We're doing the example now, right? So for this example, the gradient of f is equal to df dx df dy dz all over rho of x, it doesn't matter. So what do we have here? We have 2x1, 2x2, 2x3. It's kind of related to what we just did. That's 2 times the vector x itself. So in this case, if we're out here at a point on the sphere, then the gradient really is perpendicular to that. But we want to prove it in the general case, where instead of a sphere, we have any kind of surface. No sharp corners on the surface, right? It's got to be a smooth surface. So that's a good one, and actually very important in the theory of constraints, force constraints, essential for that. Other things as well, in fact, functions with constraints are not use of this Lagrange multipliers. There's use of this. So, do we know how to do this one? I'll give a hint here. Basically, you want to be in here. You have, so I'll just put a hint. Maybe too much of a hint, but suppose you have f of x equals c, and you're now restricted to the surface. Okay, f of x restricted to the surface gives you that constant. What you can imagine is that you have a curve, any curve that is moving, that is a parametrization of a curve in the surface. So if you do this, then you could say d over dt of f of x of t, we'll just use t as a parameter in that time, is equal to d over dt of a constant is equal to 0. actually get you to the solution really quickly, and that's pretty, you'll see that's pretty interesting. You still gotta interpret it correctly, but, this of course was an example that was available geometric right away. Yeah.
Sorry, what's the question here? I'm confused.
We're trying to prove that the gradient of f of x is perpendicular to the surface that's generated by f of x equals a constant. Just like the sphere, I did it for the sphere, and we see the gradient is just 2 times the vector itself, the radial vector. So yeah, we'll just prove this in general. Good problem. Okay. So now I'm going to shift gears to trigonometric identities. Trigonometric polynomials. In order to start doing linear algebra in the function space. I think we have time for this. This goes back to this goes back to our Fourier series now. Okay? And we're going to repeat the Fourier series discussion a bit in terms of function spaces, and then we'll try to generalize it either today or on Thursday. So here we have a collection of things to work on, so that's good too. Okay, so returning to some recall. Function space, infinite dimensional, and Fourier series. That's where we're going to return. So we'll do this. What we'll do is this. I want to approximate a function with a finite polynomial. And then it's going to be a finite trigonometric polynomial. So we're going to do this. We're going to approximate f of x by what I'm going to call f sub capital N of x. And we're going to sum just e to the I kx, k equals minus n to n. And we're going to choose the best a sub k's to make that approximation. So this isn't the entire Fourier series, but rather just a set of n minus 1 to 1, minus 2 to 2, so forth of these. We want to find what are the best a sub k. A sub k's. So in order to do this, remember we had a scalar product structure here. So what we're going to do is consider the norm of f minus f sub n squared if f were equal to f sub n, then of course this would be a 0, but it's always a positive number. So we want to minimize this expression. How to minimize? Question mark. So we'll get started on this like in the following way. So we have f minus f sub n squared. That is equal to the scalar product of f minus f sub n into itself. There's a number of symbolic steps we can do before we actually have to plug in these concrete expressions here. So this would be, and you have to pay attention to the order, this would be f, okay, minus f n, f minus f n plus fn. Those are the scalar products. And we can plug in right now. So this one is 1 over 2 pi f star of x, f of x dx. We were doing minus pi to pi, so we'll do that right there. This one here, minus 1 over 2 pi, so we'll translate it to those integrals now. And integral sum of minus n to n a sub k star e to the minus I kx f of x dx. The second one is the different order, so minus 1 over 2 pi that's pi to pi f star of x sum over x sub k e to the I kx dx, minus n to n. And the last one, which I'll put here, would be the 1 over 2 pi integral. And now we have a sum of both of these. I'm going to write both of these sums in. A sub k star minus I kx a sub k. In fact, we need a different subscript, so I'm going to use n e to the I nx. So that's k, that's n dx minus pi to pi. So what happens with each of these, I'll do that right here. So we've got the f minus f n. This one here is just 1 over 2 pi f of x complex magnitude squared dx minus pi to pi. This last one, so we have these two minus ones. This last one we actually want to deal with because we have the Kronecker delta there for those e to the minus I kx, e to the I nx. So that turns into a single sum, which I'll put down here. Remember the 1 over 2 pi e to the I kx e to the minus I nx, or the other way around, equals delta kn. simply turns into the sum a sub k, a sub k star, a sub k squared, k equals minus n to n. And so then we just have to look at these two middle ones. And I'll put those here. That should be close to that. So, minus this one minus that one, and plus k squared, k equals minus n to n. Because the next step is the minimization. So what we want to do is d a sub k star and partial c, because now we're going to minimize with respect to those coefficients in here. So of this whole thing, and we want to write down what that is. And we're in this expression here. A sub k star only appears right here. A sub k star appears right there. And when we differentiate with respect to that, we're picking off one of those terms and the integral over that. So d is equal to minus 1 over 2 pi minus pi by f my notes I have it without the star. That'd be something. I'm working on this one right here. Okay, that's good. So 1 over 2 pi f star of x e to the I kx dx. And the other one we're picking off is on this one, which we have a sub k star. So we're differentiating that one away and keeping the a sub k star. So plus a sub k star. So that's the result of that partial derivative with respect to the coefficient a sub k. And of course, we're trying to optimize this, so we're going to set this partial derivative equal to 0. And that brings out, we'll leave the left side up there. So set the partial derivative equal to 0. So equals 0, exclamation, and then we get a sub k star is equal to 1 over 2 pi integral f star of x e to the I kx dx. And if we star that again, that means a sub k is equal to 1 over 2 pi f of x e to the minus I kx dx minus pi to pi. So there's the punchline. And that's exactly the same thing we called C sub k when we started doing Fourier series. So what we see now is that these Fourier coefficients, the good old Fourier coefficients, these Fourier coefficients minimize the difference between that finite polynomial and the true function. So that's interesting in practice because it means that when you approximate with a finite Fourier sum, so you've got some function, you have 5 or 6 terms, then every term you add improves your approximation. So you've always got the best approximation for the number of terms you have. Every term you add simply improves that approximation. Because it just drives this, you know, you're minimizing this positive thing, you're just driving that thing down to zero, the more terms you put in there. Good. Yeah, we'll talk about the nature of these norms. So this is a different convergence criterion than we're used to, say, with functions. Because here we're having, remember what this norm difference is you've got minus pi to pi, you've got some function here, and you're approximating it, you know, with a few of these over the entire interval. So there can certainly be points where you don't have equality, where the integral still vanishes. Good. So we get one more interesting result out of this. Actually kind of pretty crucial. So yeah, what we did was we set this derivative equal to 0, and that just gave us the regular Fourier coefficients that we had called C sub k before. In this calculation, they were completely undetermined. They were just numbers. And now we find out what those values are. Okay, so I'll just put this as a note. Each added term improves the approximation. Let me say the note. Improves the approximation. And now if we plug these in, now we have this. Again, we're finding Fn squared. We plug in those results, we end up with 1 over 2 pi, this is the first one, f of x squared dx. And what remains is the sum over k equals minus n to n. Now I'll go ahead and call them c sub k squared the way we did before. So it's always improving the approximation. This is always positive, so this is always greater than or equal to this. In the limit, if limit n goes to infinity, f minus f sub n equals 0, then we get a very interesting identity. Then the right side is equal to 0. Then we have 1 over 2 pi f of x magnitude squared dx, which after all, that's just the norm of f squared, is equal to the sum of c sub k squared. K goes from minus infinity to plus infinity. Or I can write it this way, norm of f squared equals the sum over c sub k squared. That's Parseval's identity. Parseval's equation identity. And this is something you use in quantum, and you see in quantum. You've got your, this, for example, this could be your real space, this could be your Fourier space, and you have this identity. We say we have this when we have a complete set of functions for a certain function space. So yeah, that's a nice application. And I think I have time to do one more little application. Do these. Yeah, this here is from Griffiths. It's a good way to segue into these things without too much terminology. So now we're going to use these functions, the trigonometric, the IKX, in a differential equation setting. Slightly modified, but more or less similar. So this was a reminder of the whole idea of the function spaces, right? These were expansions of functions with an infinite set of basis vectors, those complex exponentials. And this time we'll look at a differential equation in that here. So this is an example out of Griffith's, linear operators, eigenfunctions, eigenvalues. This is the best one to blast off with, eigenvalues. So instead of matrices, we're going to have a linear operator on a function space. So what we'll look at is the space, the set of functions that are going to map 0 to 2 pi. We've been doing minus pi to pi, 0 to 2 pi, and Fourier theory is usually the same properties. Okay? So we're going to map 0 to 2 pi onto the complex numbers. Those are our functions. Actually, we have to specify a couple properties. F is square integrable. That should be no problem because we're on a finite interval. Square integrable. And it's also 2 pi periodic. This is out of Griffith's. So the operator Q hat equals the complex number I times the derivative d over d phi. Phi is our variable. And this is linear. So that's the first thing we have to know. Is this a linear operator? And if it were linear, we would have to say Q applied to alpha F plus beta G. That's going to be I d over d phi applied to alpha F plus beta. Alpha F plus beta G. And sure enough, the derivative is generally linear, so that's going to be alpha Q at F plus beta Q at G. That'll be no problem. Also, just pull the alpha through. So we have a linear operator. That took care of that. So that takes care of the linear part. So what about the eigenfunctions and eigenvalues? So the eigenvalue equation here, it's not matrix times vector. It's Q hat F equals lambda F. Of course, in this case, it's a differential equation, so we have I d F d phi is equal to lambda times F. Multiplied by minus I, both sides by minus I, we get df d phi is equal to minus I lambda F. And that is one of our exponential functions. So that's So if I want, I can normalize it. So I'm gonna name these, the way Griffiths does, I'm gonna name these phi sub k of phi, and I'll normalize it, I'll have e to the minus I k phi over root 2 pi. And at this point I have b sub k, b sub j, Kronecker delta, kj. Okay. Exactly the same as we had with our Fourier series. We put the root 2 pi, we put the 2 pi as a square root in each one of these. So we don't have the 2 pi out front anymore, but otherwise it's exactly the same. Good, I'll put this up here for the record. So now we have a general solution as a sum of c sub k phi sub k of phi, like this. Our c sub k is just phi sub k into f, scalar product. So it can all be done symbolically now, and these give us the Kronecker delta. So this is still k equals minus infinity to plus infinity. So the 2 pi periodicity has already been built in. 2 pi periodicity has been built in. So we chose our lambda to be the whole number, okay, in order to get the 2 pi periodicity. So lambda is k 2 pi periodicity. So yeah, that's all we. I'll go ahead and put the integral expression here as well. So we've got 0 to 2 pi. Instead of the 1 over 2 pi out front, we built them in e to the I k phi root 2 pi f of x dx. No, not f, phi. F of phi dt. So that's the first and most basic example, really, that you can do. Okay, you've got an eigenvector, you've got some space of functions that's defined like this. They have to be 2 pi periodic because they're living on the 0 to 2 pi interval. You have a linear operator, it's a differential operator, but it just has the same form as eigenvalue equation. You solve for it, and then you end up with your eigenfunctions. You've got an infinite set of these, and you can construct any function you want. Anything you can draw with a pencil. So the reason this one is so important is later on you're going to have much more complicated differential equations that some mathematicians have figured out for us. Okay, and then they're tabulated in books and their properties are tabulated. You solve problem sets for a property or two. But these we own, from beginning to end, we know these really well. So when you get more complicated problems in quantum, you want to go back to this one, which contains all the aspects. Just peace of mind, okay? This is the one where you can understand everything later on. You kind of just accept it, it's got the right form. And these kind of relations, you'll have in general. You'll find that I have a linear operator, a Hermitian operator. Its eigenfunctions satisfy this, and I can just knock out that kind of a expansion. Good, that's all I've got for today.